Hello, welcome to episode 10 of Generating Functionology. I'm on the exercises at the end of chapter 1. I'm still on exercise number 1. I spent a long time so far investigating parts 1a to 1e, so now I'm going to look at parts 1f and 1g. They look like they're going to be a lot simpler. So let's see. 1a, we're looking at an is 3 to the n. So what this means is we're looking at the function, let's call it fx, sum from n equals 0 to infinity, 3 to the n, x to the n. Well, it seems utterly trivial compared to what we were playing with before, so we write this as 3x to the n. And we see this is just the geometric series 1 minus 3x. Oops, I called it 1a. What are we on? 1e, is it? No, 1f. And 1g. An is 5 times 7 to the n minus 3 times 4 to the n. So sum from n equals 0 to infinity, 3 times 7 to the n minus 3 times 4 to the n, x to the n. Let's split the sum up and take the constant factor out. So 5 sum over n, 7 to the n, x to the n minus 3. Then from 0 to infinity, 4 to the n, x to the n. Just as before, we've got geometric series here, so this is just going to be 5 over 1 minus 7x minus 3 over 1 minus 4x. Easy. So let's look at question 2. Question 2 is the same sequences as in part 1. So we have to find the exponential generating function of them. So first one was an was n, and so we're going to find the exponential generating function. So we'll have fx, this is 2a, sum from n equals 0 to infinity, n over n factorial, x to the n. So let's bear in mind sum from 0 to infinity of x to the n over n factorial. This is e to the x. It's very famous power series expansion of the exponential function. So I'm sure this is going to be used a lot here. So well, n over n factorial, well, for n greater than or equal to 1, this is just 1 over n minus 1 factorial, but for when n is 0, this is 0 anyway, so I'll get instead sum from n equals 1, and it's going to be 1 over n minus 1 factorial, x to the n. As n goes from 1 to infinity, n minus 1 goes from 0 to infinity. So I'm going to sum again from n equals 0, shift the sum. So I'm going to have 1 over n factorial, and this is going to become x to the n plus 1. So I've basically replaced n in here with n plus 1. And if I take an x out, get rid of that plus 1, and this is just x e to the x, as we have this bit here is just enough from there. So that's fairly straightforward. What's b? B wants us to look at a polynomial alpha n plus beta. So B for an equals alpha n plus beta. So sum n equals 0 to infinity alpha n plus beta over n factorial x to the n. Let's split it up. We're going to get alpha, sum from n equals 0 to infinity n over n factorial x to the n plus beta x to the n over n factorial. So from what we did before, we know this is just going to be alpha x e to the x plus beta e to the x. So at the moment, all we have is it's alpha x plus beta times e to the x. So in general, for a general polynomial, is this what we're going to end up with? The original polynomial with x replacing the n multiplied by e to the x. I'm going to suspect not, but maybe that would be nice. So let's see. So the n squared, yeah, n squared. So this might give us a hint. If this continues to follow this pattern, I'll start to suspect it, but if not, so c n equals n squared. So fx, sum from n equals 0 to infinity n squared over n factorial x to the n. So when n is 0, this term here is 0, so I'm going to sum from n equals 1 to infinity n squared over n factorial x to the n, and I'm going to take an n out the top and the bottom here. So it's going to be n over n minus 1 factorial x to the n. Okay, I'm not sure I need to do this. Well, I'm going to note, I'm going to use so the fact that fx is equal to x times d by dx, what we did before, just as we were doing with the and we know that this is x times d by dx x e to the x. Yeah. So let's work out what this is. So d by dx x e to the x, need to use the product rules, so e to the x plus x e to the x equals e to the x 1 plus x. Okay. And then we multiply through by x because we're after x times d by dx. So which should be the case then, that fx, which was sum from n is 0 to infinity n squared over n factorial, is x to the n is ex x plus x squared. Now so far this is looking rather like what we had when we were looking at just the standard generating functions. We had that sum from n is 0 to infinity of x to the n was 1 over 1 minus x. Sum from n is 0 n times x to the n was x over 1 minus x squared, and sum from n equals 0 to infinity of n squared x to the n was x plus x squared over 1 minus x cubed. So these numerators currently are exactly what we multiply by e to the x. So when we had n squared, you got e to the x times this numerator. In part before, let's say when we just had n, you got x times e to the x, which is just x times its numerator times e to the x, and when n is just 1, you've got the standard exponential power series, so it's just 1 times e to the x. So far it's agreeing it's just the numerator here multiplied by e to the x. Is this going to continue to be the case or not? Be interesting to see. So let's see. So next question is it's a general quadratic. So all it's going to be, so an is alpha n squared plus beta n plus gamma. So fx, the exponential generating function, n is 0 to infinity, an over n factorial x to the n. It's simply just going to be the linear combination of the things we already found. So it's going to be alpha I'm going to take e to the x out because everything's got e to the x in, so let's get e to the x times alpha x squared plus x plus beta x plus gamma. That's all it's going to be. So as you see, we've deviated from the thing that I was hoping it might follow, where I thought maybe it'd just go alpha x squared plus beta x plus, say it's the same polynomial, so it's deviated from that already, which I suspected would be the case. So e is just his general polynomial of degree n. So as we see, if we know what, let's call fkx, same notation as we did before, sum from n equals 0 to infinity, n to the k over n factorial x to the n. If we can write this, then we can write any linear combination, i.e. any polynomial like this of degree m in terms of these fk's. So yeah, so this is what we want to look at, and we know that fkx is going to be x times d by dx e to the x. Oh, applied. So xd by dx applied k times to e to the x. So let's try and work out a couple of these. I think we're going to be spending a lot of the time differentiating stuff like this, x to the alpha times e to the x, and multiplying this by x. So let's just work this out for so that we can use this rather than working it out every time. So this is going to be x times doing the product rule, so alpha x to the alpha minus 1 e to the x plus x to the alpha e to the x, because e to the x differentiated as itself. So this is e to the x times alpha x to the alpha plus x to the alpha plus 1. Cool. So let's try and work out the first few. So we did f2, so let's look at f3. It's going to be x times d by dx f2x, which we worked out to be e to the x times x plus x squared. So using this, let's work out what this is going to be. So first coefficient, it's x to the 1, so we're going to have, for e to the x out, x plus x squared. Then for x squared it's alpha 2, so plus 2x squared plus x cubed. So this is just e to the x, x plus 3x squared plus x cubed. So now we've deviated. We're deviating again from what we had before, because we had sum from n equals 0 to infinity of n cubed x to the n was x plus 4x squared plus x cubed, if I remember right, over 1 minus x to the 4. So we're no longer getting that the numerator of this rational polynomial is this factor here. So I'm going to see if I can come up with some sort of recurrence relation then for these coefficients. So we've got quite a simple rule for generating the next one. So let's suppose then, let's define, so fkx, we know what fkx is. That's sum from n equals 0 to infinity, n to the k over n factorial x to the n. And I suspect it's going to be of the form e to the x times polynomial, which I'm going to call gkx. And fkx is equal to x times d by dx of fk minus 1x. So fkx is e to the x times gkx is equal to x times d by dx gk minus 1x. So let's write gkx using the same notation as I did before. So sum from n equals 0 to infinity of gkn x to the n. So gkn is the coefficient of x to the n of gkx. So I'm not assuming here that gkx is a polynomial, because I'm giving it the possibility of having infinitely many coefficients, and we know that this certainly exists a power series gkx which will satisfy this. It's just fkx divided by e to the x, and that can, the power series for that can be computed. So I'm not making any extra assumptions that gkx is in fact a polynomial. It could have infinitely many terms, but so I can still work with this. I'm just hoping that later it will turn out that it's always going to have finitely many terms. But we don't need to assume that gkx is a polynomial at this point. So let's see. So e to the x gkx is equal to x d by dx, and gk minus 1x is just sum from n equals 0 to infinity gk minus 1 n x to the n. This operator acts linearly, so I can move it inside the sum. N equals 0 to infinity. I feel like I've missed something out here. Yeah, I have. There should be an e to the x here, because fk minus 1x is e to the x times gk minus 1x. So I have e to the x here, and e to the x needs to be in here as well. So gk minus 1 n x d by dx, and inside this operator is e to the x x to the n. Yeah, is that right? Yeah, I think so. So now I can apply this operator here. N equals 0 to infinity gk minus 1 n. I can calculate what this term is here. So it's going to be n x to the n e to the x plus x to the n plus 1 e to the x. So what we get here is that this is equal to, I'm going to take the e to the x out, sum from n is 0 to infinity g k minus 1 n nx to the n, and then I'm going to split it up into a second part, sum from n is 0 to infinity x to the n plus 1 g k minus 1 n, and this is all e to the x gk x. As we see here, we've got an e to the x on both sides, so I can cancel these out. So we've got this relationship here, which gives us the occurrence relation for the coefficients of gkx. So I should probably organise this right hand side a bit better first. So I'm going to take this right hand sum, I'm going to shift it so it goes from n equals 1 to infinity and replace n with n minus 1 here. And I'm going to take this sum from n equals 1 to infinity, and I'm just going to get rid of the n equals 0 term, because when n is 0, this whole term is 0. So n is 1 to infinity, g k minus 1 n x to the n. And I'm going to shift the second sum, n equals 1 to infinity, g k minus 1 n minus 1 x to the n. This is equal to so sum from n is 1 to infinity g k minus 1 n minus 1 plus n g k minus 1 n x to the n. So this gives us a recurrence relation. So this is gkx for the coefficients. So it's almost like a triangle rule. So g kn is going to be equal to the coefficient of x to the n in this right hand side, which is just g k minus 1 n minus 1 plus n g k minus 1 n, and this is going to hold for all n greater than or equal to 1 and all k greater than or equal to 1. So let's use this to calculate first few rows to see if it agrees with what we calculated so far. So k equals 0 row, we knew it was just constant term 1. K equals 1, we had that it was just x times e to the x, wasn't it? So we had f0x was e to the x. So and f1x was x e to the x, and f2x was x squared plus x e to the x. Sorry, a bit messy, very messy. Okay, so let's see. Just try k equals 2 using this recurrence relation, see if it makes sense. So it's going to be this one. This is the n equals 0 row, n equals 1 row. So this one plus 1 times that, and it's going to be that plus 2 times that. Okay, that's green so far. K equals 3. It should be 1, 3, 1. So it's 0 plus 1, 1 plus 2, 1 plus 0. Yeah, it's green, so let's work out a few more. K equals 4, 1 plus 1, 1 plus, it's going to be 6, isn't it? 3 plus, so this is 1, 2, 3, 3 plus 3, 6. Then it's going to be 1 again. K equals 5. You're going to have 1 plus 14. 7 plus 3 times 6, so 7 plus 18, is that 25? 6 plus, so this is n equals 1, 2, 3, 4. 6 plus 4, 10, and it's going to be 1. So you're getting this. This looks rather like the partition numbers in K. And this recurrence relation here is very similar to what it was for the partition numbers. So let me just check if it's exactly the same. Exactly the same recurrence relation. I can't remember it offhand. If it is exactly the same, then that alone, so nk, we have nk in curly brackets is equal to n minus 1 k minus 1 in curly brackets plus k n minus 1 k, and this is exactly the same recurrence relationship. However, we've just got n and k reversed in our notation. It's exactly the same, and because it agrees for the first few, but because it agrees for n0, that's all we need. So, you know, 0, 0 is equal to 1, and n0 is 0 for all n greater than equal to 1. And this also holds true for our g's, so g 0, 0 is equal to 1 because it was just e to the x. f0x was e to the x. And g n0 is 0 for all n greater than equal to 1. I think that was all we needed. That's all we need. We just need this row here, which is just 0 is this way and 0 is that way. And we can keep applying this recurrence relationship. It's going to be exactly the same as the partition numbers. So we have a proof there, that'll do, that fkx is equal to, well, it's e to the x times gkx, and what's this? So gkx is e to the x, sum from n equals 0 to infinity gkn x to the n. And gkn, well, it's just e to the x, sum from n equals 0 to infinity of kn in curly brackets x to the n, and it appears to be that's that. And so for n greater than k, you can't partition k into any more than k classes. This coefficient is 0, so it's e to the x times sum from n equals 0 to kn in curly brackets. And I think that's a good enough form. If I remember rightly, there wasn't a nice simple way of expressing this as, or we didn't cover a nice simple way of expressing this polynomial as a single polynomial. I mean, it was a polynomial, and we only had a differential, like keep applying, you know, x times d by dx. We had some sort of derivative rule. We had a derivative operator that we kept applying to the polynomial to get the next one, but we didn't have a formula directly for it. So I'm going to leave it as that format. I'm happy with that. That's very compact and nice. And yeah, assuming I haven't made a mistake, I'm imagining that that's right. I've almost finished question 2 then, depending on how difficult the next the next part is going to be. In fact, I suspect it's going to be easy for f and g. So let's have a look. F. So f was 3 to the n. So I'm happy that I've covered the polynomials now. I mean, we've done fk, and then any polynomial is just going to be a linear combination of these fk's. So let's look at f. So 2f. Three to the n. So an is 3 to the n. This is going to be easy, isn't it? So we're going to have sum from n equals 0 to infinity an over n factorial x to the n. This is sum from n is 0 to infinity 3 to the n x to the n over n factorial is okay, and this is sum from n is 0 to infinity 3x to the n over n factorial. And now since e to the x is sum from n is 0 to infinity x to the n over n factorial, e to the 3x is going to be 3x to the n over n factorial. So this is just e to the 3x. Easy. 2g, we had, this is exactly the same, except we've got a linear combination, 5 times 7 to the n minus 3 times 4 to the n. So it's just going to be 5 times e to the 7x minus 3 times e to the 4x. Work out exactly the same way, won't it? So that's fairly straightforward, that. So yeah, that's question 1 and 2. I've attempted to do them. It might be worth having a look at the solutions. So here we are, I've got the solutions up. So seems to be a bit of a cop-out. So let's see, the first one, yeah, they've got x over 1 minus x squared. Yep. And for linear polynomial, they've got alpha x over 1 minus x squared plus beta 1 minus x. Yep. And for C, they've not even written out what it is. So, you know, we worked out it was x plus x squared over 1 minus x cubed. All they've written is that this is d dx x applied twice to 1 over 1 minus x. And they've not actually worked out what it is. I think that's a bit of a cop-out. It's very easy to work out what it is. And they've left it in the same form for part D. And for part E, that's where it's the biggest cop-out of all. They've literally just written, oh, you know, you apply x times d, dx. X times d, where d is d by dx, applied to 1 over 1 minus x. Well, yeah, but you know, that's not a very convenient form. Try working out from that the 20th, you know, the 10th even, you know, or even the 4th or 5th. It's going to be a right faff calculating that out. For f and g, we got the same thing, 1 over 1 minus 3x and 5 over 1 minus 7x. Yep, that's all the same. So they've not really, I guess I put far more work into part E than was expected. There we are. But you know, so I've done my own work, which I think is quite nice itself. But they haven't done that. They haven't put that in their solutions anyway. They've just written it in that form. So they were happy just to accept an equation involving a differential operator raised to some power, which I thought was not what they were after, but that's fine. I just did more work. I did my own stuff. So let's see if my answers are the same for part 2. So got x e to the x for part A. Yep, that's what I got. And then they've got the linear form of it, alpha x plus beta times e to the x. And then for c, they've got the same as me, x plus x squared e to the x. Yep, that's the same as what I got. And then they've got it expressed linearly, and now they've just put it back into the x times d applied twice form. Apply it to e to the x. And the same part e, they've been lazy again, and they've not done the same work that I did, where I actually calculated what the coefficients of the polynomials are going to be, and f and g, yeah, they're the same. So I've done far more than was expected of me for these two questions. So yeah, some new stuff there in my videos that wasn't in the book. So hopefully you enjoy that. So I'm going to go on to question 3 now. So if f is the ordinary power series generating function of a sequence an, so fx, what this means is fx is the ordinary power series generating function, so sum from n is 0 to infinity an x to the n. Just write that down so it's clear what we're talking about. Then expressed simply in terms of f, the ordinary power series generating functions of the following sequences. In each case, the range of n is 0, 1, 2, and so on. And I see that question 4 is the exponential version of question 3. Okay, so question 1 and 2. Question 2 is the exponential generating function version of question 1. Question 4 appears to be the exponential generating function version of question 3. So let's try this out. So A, we've got an plus c. So we want to look at sum from n equals 0 to infinity an plus c x to the n. I'm going to split this up. Sum from n is 0 to infinity an x to the n plus sum from n is 0 to infinity c x to the n. C is a constant. And this part here is fx. And this part here, it's just geometric series, ratio x. I'm going to put c on the outside. So this is fx plus c over 1 minus x. Okay, there's that. That part is easy. Question B. Now we have a constant multiplier, so we were looking at alpha an plus c. N equals 0 to infinity. So again, this is, we can just expand this out a little bit. We could take the constant alpha out. Sum of n 0 to infinity an x to the n plus c. Sum from n equals 0 to infinity x to the n. And this is just alpha fx plus c over 1 minus x. Okay. Question C. What you have now is na to the n. Sorry, nan. So we're looking at this. And this, I'm guessing, all they want from this is that this is the derivative of f. So the derivative of f is d by dx. Fx is d by dx applied to fx, which is this. And that is just d by dx. Whoops. We can apply this, so it's just a sum from n equals 0 to infinity an n x to the n minus 1. And if we multiply this through by x, then you get this here, and this is precisely what we're after here. So this is just x d by dx fx. I suspect that's exactly it. That's all I want. Part D, they have Pnx, so sorry, Pn an x to the n. Sum from n is 0 to infinity. So yeah, they just want us to do it like the solution that they gave to question 1 part E, I think it was. So if our polynomial Pn is some, say it's degree m, sum from I equals 0 to m. Actually, I'm not going to use m, I'm going to use big N, because my m's and n's sound the same. The sum from I equals 0 to big N, let's call it pi n to the I. So it's a degree big N polynomial. These are the coefficients of it. So what we're working out here is sum from n equals 0 to infinity, sum from I equals 0 to infinity, pi n to the I an x to the n. I'm going to swap the order of sums here. Sum from I equals 0 to infinity, and I'm going to take the pi out, and we've got sum from n equals 0 to infinity of n to the I an x to the n. And this bit here is fx with all of the coefficients multiplied by n to the I. So this bit here is d, so it's x times d by dx applied to fx I times. So just a bit in here, sorry, shouldn't include the sum in the brace there. So it's x times d by dx applied I times to fx. So what we have is that this is, I'm going to write it in that form, so it's sum from I equals 0 to, it shouldn't have been I to infinity, it should have been I to big N, because a polynomial is of degree big N. So sum from I equals 0 to big N, pi x d by dx applied I times to fx, which we can write as sum from I equals 0 to big N pi times x times d by dx to the power of I. So this whole thing is now an operator because it's a sum of n plus 1 operators all applied to fx. And here we can think of this as simply polynomial p applied to the operator d by dx applied to the function fx. So that's the solution they're going to be after, and that's why that's how to explain that you just put the operator x d by dx inside the polynomial. It's just shorthand for this sum of n plus 1 operators. That's going to be the answer to that question. So question E. Now the sequence we're after is 0, A1, A2 and so on. So we've basically changed A0, this now becomes 0. So F was sum from n is 0 to infinity an x to the n. Well, we can calculate A0 by calculating f for x is 0. This is just a0. So what we're going to have here is, so fx is this, I can split this sum up, so this is just a0 plus the sum from n is 1 to infinity an x to the n, and this is the thing we were trying to calculate, and that is just simply fx minus a0, so fx minus a0, and this is fx minus f applied at 0. And that will do for that one. Let's look at f. Okay, so now what we want is 0, 0, 1, a3, a4, a5 and so on. So this is 0, 1, 2, 3. So fx is sum from a0 to infinity of an x to the n. This is a0 plus a1x plus a2x squared plus sum from n is 0 to n is 3 to infinity, sorry, an x to the n. So we need to somehow calculate what a1 and a2 are to work out what this bit is. So let's see, so we know that a0 is equal to fx, where x is 0, so f applied at 0. How can we calculate a1? Well, I think we can use Taylor's formula for this. So Taylor's formula involves repeatedly differentiating our function f. So let's see, so d by dx of f is going to be sum from n is 0 to infinity n an x to the n minus 1, and I can sum this from n is 1 because when n is 0 this is 0, and then I'm going to replace n with n plus 1 and sum from n is 0 instead. So this is a sum from n is 0 to infinity n plus 1 an minus 1 an plus 1, sorry, x to the n. So this is the derivative of f. If we calculate the derivative of f at x is 0, so alright, so f prime at 0 is the constant term of this, so 1 and 0 plus 1 plus a 1, so it's a1. So that's a way of calculating a1. How about a2? So I'll put that a1 here. So we've got a0 is f0, a1 is f prime applied at 0. And a2, well, let's differentiate it again. So we have that f prime of x is sum from n0 to infinity n plus 1 a to the n plus 1 x to the n. So if we differentiate this to get f double prime of x, we're going to have sum from n is 0 to infinity n plus 1 a n plus 1 x to the n minus 1. So I'm going to, so since this is 0 when n is 0, take the sum from there. from n is 1, and then I'm going to shift sum so that I'm summing from n is 0 to infinity, and we're going to get n plus 1, n plus 2, a n plus 2, x to the n. And if we compute f double prime at 0, we're going to get 1 times 2, so 2, a2. So a2 is f double prime applied at 0 over 2. And if you continue this, then Taylor's formula tells us that the kth derivative of f applied at 0 is equal to k factorial times a k. And that's how you can calculate the coefficients by Taylor's formula. So what we're going to have here, so if we take this back, this term here is f double prime 0 over 2. So what this gives us is that the sum from n equals 3 to infinity of an x to the n is fx minus f0 minus f prime at 0 minus f double prime at 0 over 2. But this isn't quite the thing we're after, because they're asking for the coefficient of x squared to be 1, because the sequence we're after is 0, 0, 1, a3, a4 and so on. So what we need to do is add an x squared. So this is the thing we're after, and we just add a x squared here. So there is the solution. So that was question F. Now we're on to G. Now G looks interesting. So G, we're only taking every other. I'm not quite sure how this is going to come out. A0 and 0. We're making all of the odd coefficients 0. So A4, 0. A6, 0. Now this is, I'm not quite sure how we're going to split this up into 2. So, not sure how we'll do that. So fx is the sum from n is 0 to infinity of an x to the n. Now is there a way I can just get the even coefficients of this somehow? What do I need to do to f to do that? Well, and the first thing that comes to my mind is calculating f of x squared, but this doesn't quite get us, doesn't really get us what we want. What it gets us, so f x squared, sum from n is 0 to infinity of an x to n, this ends up giving us a sequence a0, 0, a1, 0, a2, 0, because all of the powers of x are even powers of x. But the sequence we're being asked to find is retaining the original a2, a4, a6. So I'm not really sure how to do this in an elegant way. I mean, other than simply just plugging in Taylor's formula and doing an infinite sum, but I don't think that's elegant enough. You know, for example, we could just say, if we're only interested in even, you know, coefficients, you could just say, well, what we're after is the sum from n equals 0 to infinity of, well, what we're after is a 2n x to the 2n. This is what we're after. and I think I might have an idea actually. Yeah, I think I've got an idea. I think I've got a better idea. So fx is sum from n is 0 to infinity an x to the n, and f of minus x is sum from n is 0 to infinity an minus x to the n. Now if we sum these together, fx plus f minus x, what we're going to get is sum from n is 0 to infinity an x to the n times 1 plus minus 1 to the n. Now 1 plus minus 1 to the n is going to be 2 if n is even, and 0 otherwise if n is odd. So therefore what we have here is a sum from n is 0 to infinity of so let's take it over the odd ends and the even ends. So n is 0 to infinity n even an x to the n 1 plus minus 1 to the n, plus the sum from n equals 0 to infinity where n is odd, an x to the n 1 plus minus 1 to the n, and this is going to be 2 and this is going to be 0 because n is even here, so this is always 2, n is odd here, so this is always 0. So what we end up with is the sum over even n. So let's say n is 0 to infinity a 2n x to the 2n, but this is 2, so we've got twice the thing we're after. So the thing we're after is going to be half of this value. So this is the thing we're after. It's equal to fx plus f minus x over 2. There we are. I like that. That was a cool one. H, all we are doing is we're getting rid of A0 and we're shifting sequence, so A1, A2, A3. Well, okay. So if fx is this thing, so sum from n is 0 to infinity an x to the n, we can remove the constant term just as we did in part E. Yeah, but this is fx, this is f applied at 0 plus the sum from n is 1 to infinity. So we can divide now. So therefore fx minus f0 is sum from n is 1 to infinity an x to the n. Now this is x times the thing we're after, because this is x, the sum n is 0 to infinity a n plus 1 x to the n, and this is the power series we're trying to calculate. So the answer we're looking for here is, so the thing we're after is this, sum from n is 0 to infinity an plus 1 x to the n. This is going to be fx minus f0 over x. So we're asking for a shift where h is a constant. So after an plus h, where h a constant. Well, it much depends whether h is a positive constant or a negative constant, because if h is not positive, then all we need to do is multiply through by x to the h. So in that case we'd have x to the h fx because that would be sum from n is 0 to infinity a n x to the n plus h. Sorry, we need to multiply through by x to the minus h. And this is going to be a non-negative power because h is non-positive. And so let's see. So the powers here begin at minus h. That's the first. So x to the minus h is the first non-zero coefficient here. So what this would correspond to would be, so say if minus h was a positive number, so it's non-zero, you would have zeros, minus h of them, and then you would get a0, a1, a2, and so on as your sequence here, because this would correspond to the x to the minus h coefficient. This is the 1x, coefficient of 1 at x, and so on. So if h is negative, it's fairly straightforward. If h is positive, which is probably what we're supposed to assume, what we'll need to do is sort of the Taylor's formula trick that we did before. So an plus h, well if h is 0, nothing changes. If h is 1, then all we need to do is remove the constant term and divide by x. If h is 2, we need to remove the first two terms, a plus a1x, and then divide the whole thing by x squared. So what we're going to need to do is we're going to need to go fx minus sum from I is 0 to h, ai, x to the I, and then we need to divide by x to the h. And this is going to be the thing we're after. But we're not supposed to just use the ai's, we're meant to write this in form in terms of fx, so then we can do that using Taylor's formula. So minus fx minus the sum from I 0 to h, f, the ith derivative of f, applied at 0, divided by I factorial, x to the I, all over x to the h. So I think that's the best we can do really, without knowing more about f. So j, what we have here is a combination. Is there perhaps a nicer way of writing this? So is there sort of like an operator? Operator that we can apply to the function f to get this form? Probably. Probably there is. Well, I'm not sure what form they're going to be writing it in the solution, but let's see. Let's go on to the next question. So j. an plus 1, sorry, an plus 2 plus 3an plus 1 plus an. And because these are going to go across linearly, what this is going to be the sum from -0 to infinity an plus 2 x to the n plus 3, sum from -0 to infinity an plus 1 x to the n plus sum from -0 to infinity an x to the n. And we know what these things are from what we've just done. So this here is fx minus f0 minus f prime 0 over, so that's going to be over 2 over x squared. I think here, when I did in the last part, was it the last part? Was it? Oh, sorry, it was on the back of this page. I think I should have done this only to h minus 1. Yeah, because we still want to keep the x to the h. We still want to keep ah. We don't want to remove that. Yeah, so that should have been h minus 1 there. So that's that bit, and then we're going to have plus 3, so it'll be fx minus f0 all over x plus, and this is just fx. Is there any way we can write this in a nice form? If I multiply through by x squared and try and collect the fx's, the f zeros and the f prime zeros, let's see what we get. So this would be x squared, well, 1 over x squared, take the 1 over x squared out, fx, so it's going to be 1 plus 3x plus x squared, and then this is going to be, well, we're going to be minus 1 over x squared times f0 applied at 0 plus 3x f applied at 0. Okay. And then also minus 1 over x squared f prime at 0 over 2. I don't see a nice simple way to write this out, so I'm just going to leave it in this form, I think. Yeah, I think so. And part H, it's just another variation. Oh, sorry, part K, it's just another variation on part J, really. So we have an plus 2 minus an minus 1 plus 1, sorry, minus an. So just like we did then, it's going to be fx minus f at 0 minus f prime at 0 over x squared minus fx minus f0 over x. Sorry, this should have been over 2 there, I think. No, that shouldn't be over 2. You only put it over 2 when it's a double derivative. So yeah. And then minus fx. So, fair enough. There we go. Perhaps you can write it a little more perhaps it's possible to write it a little more nicely. So if you consider, so take this one for example, x squared minus x minus 1 times fx. So perhaps I want to do it the other way around. Perhaps I want to do 1 minus x squared fx, I think. Then this is going to be a0 plus a1x plus a2x squared plus, this is the fx bit, and then we've got minus x fx, so it's going to have minus a0 x minus a1x squared and so on, and then we've got a x squared, so you're also going to have minus a0 x squared and so on. So, and the thing we want is this polynomial, is this power series beginning at this term here, this part here. So we want to remove these three bits and then divide by x squared. So all we really need to do for that is, well, if you defined, g as g, so gx as this thing here, then what we'd be after would be gx minus g0 minus g prime at 0 over x squared. So maybe that's an easier way to think about it, I don't know. So yeah, that was question 3. So that question and the question before has taken much less time than I spent on question 1 at first, so I'm guessing these questions are going to speed up now and probably all going to be fairly quick. And that was a fairly tedious problem, to be fair. But it'd be interesting to see how they write it out in the solutions. They're going to do question 4 before looking at the solutions again. So there we have it. I'm going to stop now because it's been going on for a while. Thanks for watching. Well done if you've watched all the way this far. And see you in part 11.